Hi guys, into lesson 3 for applications of exponents and logs today, how to evaluate logarithms. So basically what we're talking about here is to figure out the value of a logarithm. We're going to see how to do that algebraically today. So just as a review to start, they talk about the comparison between a graph like this, y equals 2 to the exponent of x, which is an exponential function, and the graph y is equal to log base 2 of x. So remember that when we're comparing those graphs, okay, they are reflections of each other in the line y is equal to x, and we are talking about their equations, okay, they are inverses of each other, which means the x's and y's are interchanged. So again, the domains and ranges are also interchanged. Again, just as a review, they go through a couple points here talking about the 0.38. Again, this is an x value and this is a y. So when I substitute them into the equation, there's the x value of 3, there's the y value of 8, and obviously 2 cubed is equal to 8. When I take the opposite point, okay, interchanging the x's and y's, the 8 is now the x and 3 is now the y. When I substitute those into the log equation, okay, the y value here is 3, and there is the x value of 8. Okay, so log base 2 of 8 has a value of 3. Okay, so these two forms, 8 equaling 2 cubed and 3 equaling log base 2 of 8, those are equivalent. Okay, moving down here, we're going to talk about, and again, they give us some steps here, how to evaluate logarithms. So it says Kelsey was asked to evaluate log base 2 of 8. Her work is shown below. Study her work and describe each step on the lines provided. So the first thing that they do is they basically take the log expression, log base 2 of 8, and they make it equal a variable, okay? They use v, so we'll use that consistently throughout the lesson today, but you can use any variable obviously you want. Now, in the next step, okay, so step 2, which is right here, they want us to write down on the line what they've done going from step 1 to step 2, and all that we've done from step 1 to step 2 is we basically changed it, or changed the equation to exponential form. Okay, so we changed it to exponential form, and again, this is what we basically learned how to do last day. Okay, from here, what we do now is the following. I take the number 8, okay, and I write it as a power that has the same base as what's on the other side of the equation. Okay, so we just say that we are making a common base. Okay, and again, I think that was lesson 1. Okay, how to write powers with common bases. Okay, from here, okay, we know when we solve the equations, once I have the same bases, then I can just equate the exponents. So v is equal to 3, so equate the exponents. Okay, and from then, therefore, I know v is equal to 3, okay, and v was the value at the very top, so v is equal to 3. So we just replace v by log base 2 of 8. Okay, so basically the idea is log base 2 of 8 has a value of 3. And there you go. So using that same rationale, okay, when I move on to evaluate the following equations, okay, or expressions, so same basic idea. If I want to know what log base 3 of 81 is equal to, okay, the first thing I do, rewrite the expression and make it equal an unknown variable. And again, I'll use v throughout the lesson today. Okay, next step is to change this into exponential form. So 3 to the exponent of v will be equal to 81. Okay, now I try and create powers with the same base. So 3 to the exponent of v will be equal to, so I want to write 81 as a power at the base of 3. That's 3 to the exponent of 4. Okay, and at this point, now I just have the same bases, so I equate the exponents, so I can say v is equal to 4. And remember, this is what v was up there, so that has a value of 4. So therefore, okay, you can now state that log base 3 of 81 is equal to 4. Okay, and there's your answer. B, same kind of idea. So I take the expression log base 4 is 64. I want to know what it equals. I'm unsure of what it equals, so I just make it equal an unknown variable. And again, we're using v. I convert to exponential form. So 4 to the exponent of v is equal to 64. Okay, I want to write 64 as a power that has the same base as what's on the other side. So that's going to be 4. So 4 to the exponent of 3 is equal to 64. Now I can equate the exponents. v is equal to 3. And therefore, I just state again that log base 4 of 64, therefore, has a value of 3. Okay. C, same basic idea here. So log base 7 of 7 will equal v. So 7 to the exponent of v is equal to 7. Now, they already have the same base, so I just write this as 7 to the exponent of 1. Okay, and then v is equal to 1. So therefore, log base 7, so log base 7 of 7 is equal to 1. Now, in this question, you probably want to put a star beside it. What you'll notice is that the base and the argument are the same number. So whenever the base and the argument are the same number, your answer, okay, is always going to be 1. All right, D. Log base 12 of 1 equals v. So 12 to the exponent of v is equal to 1. Now, these are sometimes tricky, but what I have to do is basically write 1 as a power with a base of 12. So I know that's 12 to the exponent of 0. Remember, anything to the exponent of 0 will give me a value of 1. So in this case, v is equal to 0. Okay, so therefore log base 12 of 1 will equal 0. Now in this question, again, another important thing to note is that whenever the argument, okay, has a value of 1, the answer will be 0. Okay. At the bottom of the page, okay, it says the examples shown above show that the value of the logarithm is the power to which the base has to be raised to be equal to the argument. And then they give the examples that we basically just went through. Okay, so again, anything that's bolded here, so this I would highlight just to make sure that we are aware that that's important moving forward. Okay. Now, two examples here that basically deal with C and D that we just did. So what you'll notice in these examples here is that the argument is 1 here, and in the next example, the base and the argument are the same value. So that's kind of the key here. So again, I go about solving them the exact same way that I did the last page. So I'll just go log base b of 1 is equal to v. I'm not sure what it equals. Then I convert to exponential form. So b to the exponent of v will equal 1. Okay, well, that's the same thing as saying b to the exponent of 0. So in this case, v is equal to 0. Okay, so again, now you can make your statement that log base b of 1 basically has a value of 0. And that's what we determined on the last page, that whenever the argument is 1, the value of the log will be equal to 0. In B, okay, the value or the answer here should be 1 because the base and the argument are exactly the same. So we'll just double check. So log base b of b is equal to v. B to the exponent of v is equal to b, which is like saying b to the exponent of 1. So from there, okay, equate the exponents. V does equal 1. So again, therefore, log base b of b is equal to 1. Okay, just like we thought. So those two questions go with these 2 points, okay, which are right here. The log of a number to the same base is always equal to 1, and the log of 1 to any base is equal to 0. So that's dealing with those 2 examples that I said above. Okay, so just moving on, more examples that kind of deal with the same thing. They just get a little more complicated in terms of the calculations that we're going to be doing. All right, so what I do in this case is I just deal with that number 2 on the outside. So it's like 2 times log base 8 of 512. Okay, so that's what the 2 in front of the logarithm means. So I'll just keep that 2 on the outside the whole way down, and I'll deal with the logarithm inside kind of separately first. So this is like log base 8, 512 equals, and I don't know what that equals, so again, I make it equal a variable. So this will be 2, and then log base 8 of, oops, I should go like this, actually, guys, convert it to exponential form first, okay? So this will be 2 times, and now I can go 8 to the exponent of v equals 512. So 8 to the exponent of v will be 8 cubed, gives me 512. Okay, so from here, you can see that v will be equal to 3. So remember v, okay, was log base 8 of 512. So basically, this is now like saying 2 times 3, okay, which will equal 6. Okay, there you go. There's the first one. Okay, second one, start the same way. Log base 2 of, and your argument this time is 1 over 32. So that equals v. Make the whole expression equal an unknown variable. Convert it into exponential form. So 2 to the exponent of v equals 1 over 32. Now the number 32, okay, you can see is actually 2 to the exponent of 5. The issue here is that 2 to the exponent of 5 is in the denominator. So I want to bring that up to the numerator, but when I do, I have to make that exponent negative. Okay, now I can equate the exponents. So v is equal to negative 5, and therefore, okay, you can just say that log base 2 of 1 over 32 equals negative 5. All right, last one in this little group here. So same way that we start, log base 5 of square root 125 will equal, okay, an unknown variable, which again we'll use v. So 5 to the exponent of v will equal the root of 125. So the square root, again, of 125, okay, is like saying or raising something to the exponent of 1/2. Now the number 125 is actually 5 cubed, isn't it? So 5 cubed is 125, and it's still to the exponent of 1/2. So 5 to the exponent of v will equal 5 to the exponent of 3 over 2. So v is equal to 3 over 2. And therefore, I can just state that log base 5 of root 125 is equal to 3 over 2. And there you go. Okay, so 3 different examples that kind of deal with different ways that the expression is notated, but same kind of process in terms of solving them all. Okay, in the next ones, okay, again, they're doing the same thing, but again, the instructions just say evaluate, so they want the value of the log expression, okay? So when I want to solve it, no different, log base 1 over 3 of 27 will equal, okay, and it's going to be v. So I now convert this into exponential form, so 1 over 3 to the exponent of v will equal 27. So I'm going to take the 1 over 3 on the left-hand side, and I know 1 over 3 is actually 3 to the exponent of negative 1. Okay, so I replace 1/3 with 3 to the negative 1. It's still raised to the exponent of v. So this will now be 3 to the exponent of negative v, and now I'll write 27 as 3 cubed, right? Powers that have the same base. Equate the exponents. Negative v will be equal to 3, so v is equal to negative 3. Okay, so there's the value of that log. So again, after that, you can just now say or make your statement that log base 1 over 3 of 27 equals negative 3. Okay. In B, all right, so the issue in B is that this is what I need to figure out, is the value of the exponent, because it's 4 to the exponent of log base 416. So it's going to be like this. I'm just going to deal with this part first. So I'm going to say, okay, log base 4 of 16 equals, okay, an unknown variable. So 4 to the exponent of v is equal to 16. 4 to the exponent of v equals 4 squared. So v is equal to 2. So that log base 4 of 16, okay, this equals 2. Now, I still have this 4 here, okay? So it's going to be 4 to the exponent of 2, which is 16. Okay, and there's your final answer. So you now say, therefore, 4 to the exponent of log base 416 is equal to 16. All right, the last one. So in the last one, we have to basically figure out two calculations separately because I'm subtracting two log expressions, okay? So I have to figure out this and then subtract this. So I need to know what those two separate values are going to be. So let's deal with this one here first, okay? So I'm going to go log base 1/2 of 1 over 8 equals v. So 1/2 to the exponent of v will equal 1 over 8. Okay, like so. So from here, I can say that this is 1/2 to the exponent of v, and I can write 1/8 as 1/2 cubed, okay? 1 cubed is 1, and 2 cubed is 8. So I now have the same base, which is 1/2, so I equate the exponents, so v is equal to 3. Okay, so that's what the first log expression is equal to. The second expression, okay, which is this one here, okay, again, I'll do this one in blue just so you can see it and we can kind of keep it separate. This is going to be log base 1/2 of 8, okay, and again, I'll make that equal v. So 1/2 to the exponent of v is equal to 8. Now, this 1/2 I'm going to turn into, again, 2 to the exponent of -1. So there's your 1/2, still to the exponent of v. So this will be 2 to the -v equals 2 cubed. -v equals 3, so v will equal -3. Okay. So now, the answer to this question is 3 minus -3, okay, which is 6. Okay, when we subtract a negative, it's like you're adding. So the total value of that whole expression is equal to 6. Okay, good. Next, so a little bit of stuff on our calculator. Now it says a calculator can be used to determine the value of logarithm, and again highlight if the base is 10 or e. Okay, so first off, common logarithms. Now we've taken a look at this before. When we talk about common logarithms, okay, those are logarithms that are base 10. So a lot of times they won't even write this base 10 that you see right there. They'll just write that as log of 1,000, and that's basically what they're talking about right here, okay? Log base 10 of 1,000 is the same as log 1,000. So if you do not see a base, okay, we assume that the base is 10, okay? And you can evaluate this on your calculator by just using the log key. So all you would do is go press log 1,000, enter, and you'll get the value of it. And that's kind of what they're going to ask us to do here. Evaluate log 1,000 by converting to exponential form. So they'll show you how to do this again algebraically. So if I was going to figure out log 1,000 and I wanted to know what the value of it, again, I would make it an equal to an unknown variable. Now what you want to remember here is that even though you don't see it, there is a base of 10. That's the key to this question. So now when I go and convert to exponential form, it's 10 to the exponent of v equals 1,000. So 10 to the exponent of v is equal to 10 cubed. So v is equal to 3. So there's the value of that expression, okay? The value of that logarithm is 3. Now, if I go on my calculator and I want to evaluate on my calculator, I simply go log 1,000, okay? Enter, and you will see that that basically has a value of 3 as well. Okay, so same value using the calculator and solving it algebraically, but again, that works because I have a common base of 10. Now, natural logarithms, okay, so natural logarithms have a base of e, okay, and you'll see that right here in this question, log base e of 15. So again, I can write log base e of 15 as ln 15, a natural log of 15. So those two are equivalent. I can write it either way. And if I want to evaluate that on my calculator, I use the ln button on my calculator, which again is just basically between the 7 and the 4 on the left-hand side of your calculator. So evaluate the following logs to one decimal place where necessary. So the natural log of 5. So again, all I would do is turn my calculator on and then go ln 5, enter. Okay, and you will get to the nearest tenth, 1.6. Okay, in this second question, okay, when they have log base e, well, we know that's the same as the natural log of 5. So again, ln 5, enter, and again also 1.6. Okay, so A and B are basically the same question, just notated two different ways. And then in the third question, which is C, I'm going to go ln of E. Okay, and the E is located right above the division sign on your calculator. Okay, so ln, second function, division to access that E, enter, and you'll see you get a value of 1. Okay, so just some calculator work there in terms of how we use it when we have common logarithms or common bases. Okay. Now, the next page, okay, evaluating logs when we change the base. So it says, try to evaluate log base 5 of 50. What problem do you encounter? So if I was trying to evaluate this based on what we've done so far in the lesson, this is what it would look like. Log base 5 of 50 equals v, right? An unknown variable, I'm not sure what it equals. 5 to the exponent of v will equal 50. And now here's the problem, okay, that they are talking about, is that I cannot write 50 as a power with a base of 5. So that's kind of what they're asking you to write down. If you want to write that down, great. If you don't, you understand that problem, then obviously you don't need to write it down, but I'll just write it here for you guys in case you want it. So 50 cannot be written as a power with a base of 5. Okay, can't happen. Now, in part B, it's kind of like a multiple choice question. It says, choose the correct alternative. The exact value, okay, of log base 50 is what? Well, it's not going to be between 1 and 2 because 5 to the exponent of 1 is 5 and 5 squared is 25. Those numbers are too low. They're not at 50. 5 squared is 25. 5 cubed is going to be 125. So this is going to be your answer, okay? It's going to be somewhere between 2 and 3. Okay? Now, it basically tells me nicely in the next step what I wrote above. Okay, we are unable to evaluate log base 5 of 50 by converting to exponential form. We can, however, evaluate the log using a calculator by changing the base to a base that the calculator recognizes. Now remember, the bases the calculator recognizes are 10 or e. Okay, and that's exactly what they're saying here, base 10 or base e. So now we're going to take a look at how we do that. So we want base 10 or base e because then we can use our calculator to evaluate the log. So in part A, evaluate log base 525 by converting to exponential form. So this one we'll be able to do. Log base 5 of 25 equals v. So 5 to the exponent of v will equal 25. 5 to the exponent of v will equal 5 squared. Okay, so v will equal 2. Okay, therefore, okay, log base 5 of 25 is equal to 2. Okay, so there's our answer. In part 2 of A, it says evaluate now using log 25 over log 5 and natural log of 25 over the natural log of 5. So regardless if I go log 25 divided by log 5 or natural log 25 divided by natural log of 5 with my calculator, you will find out that both of those calculations also equal 2. Okay, and again, I can use my calculator for both of those calculations because in the first calculations, the bases are 10 there, and then the second, remember, natural log is the same as using log base e. Okay, so again, that's why I can use my calculator. Part 3 here says comment on your answers from 1 and 2. We just say they're exactly the same. Okay, we got 2 whether I solved it algebraically in the first part or I used my calculator in the second part. Okay, example B. Almost identical, just using different values. Okay, so we're going to go log base 3 of 243. I want to know the value of that. So again, I make it equal an unknown variable if I'm unsure of the value. So 3 to the exponent of v will equal 243. So 3 to the exponent of 3, 243 will be 3 to the exponent of 5. Okay, so v will equal 5. Okay, so my original question, log base 3 of 243 has a value of 5. Okay, that's the answer I'm after. So again, in the second part now, when I evaluate log base 243 over log 3, okay, so this calculation here, okay, or I use log base e of 243 over log base e of 3. Now remember, log base e is the same as the natural log. So you can go natural log of 243 over the natural log of 3. And again, in both of those, you will see the answer is also 5. Okay, part 3, comment on your answers. Again, you can just say that the answers are the same. Now in C, it says, in the first part of this lesson, we learned that log base 2 of 8 was equal to 3. Okay, so remember 2 to the exponent of 3 equals 8. Okay, that's how we convert from log form to exponential form. Write log base 2 of 8 in a form which can be evaluated using a calculator. So if I wanted to, evaluate this on my calculator, I simply go log 8 all over log 2. Okay, so it's always log of the argument over log of the base. And I've now created a situation where I can use my calculator because I've changed the base to what? Either 10, okay, which I would write in here, okay, or base 3. It doesn't really matter, okay, which way you think about it, but the base is the same, okay? So it's 10. So again, when I do that, again, you will see that when I figure out that value on my calculator, okay, it will also give you 3, okay? Same idea in the next example, log base 2 of 64. So if I want to use my calculator, again, I can use natural logs or base 10, but it's going to be the log of the argument all over the log of the base. Okay, so it's log 64 over log 2. So on your calculator, just log 64 divided by log 2, and you'll see the answer there is 6. Fantastic. Okay, so on the next page, it takes us to basically what we call the change of base identities, and those are just the rules that we were following in the last couple of examples on how to evaluate using our calculator. So if you take a look at the first one, when I have log base b of x, so again, I'm just dealing with this box right here, it's log of x, so log of the argument over log of the base. Okay, so log x over log b, or if I want to use natural logarithms, the natural log of x over the natural log of b. Okay, so the important things here with the guy with the fake stop sign, it says the above identity is used for converting logs to, again, base 10 or base e. So that's what we use our calculators for. This identity can be extended to bases other than 10. So you can use any base you really want. Here they use a base of a, but you're going to want to stick to 10 or e for the most part because, again, like they mentioned, it's easy. We can use our calculator to help us evaluate in those cases. Says, for example, log base 4 of 1024 can be valued by converting to base 10. And you can see it's log 1024, so log of the argument over log of the base, which is what they've done here, okay? And again, you don't see the base there, so they've used a base 10. Or if you really wanted to, you could change it so it's base 2, but again, log of the argument over log of the base, and you can put whatever base here you want, but we stick to 10 or e because, again, we can use our calculator. Moving on, evaluate the following logarithms by changing the base. Round off, okay, to the nearest hundredth, so 2 decimal places. And again, when we read carefully, okay, where necessary, again, meaning if I don't have to, then I don't have to round to 2 decimal places. If they wouldn't have used the phrase where necessary, then all my answers would have to be to 2 decimal places. But because of that last little phrase where necessary, if it's a perfect whole number, then there is no rounding that needs to be done. So evaluate by changing the base. So right now the base is 4. Okay, I want to use a base that I can that's more friendly and allows me to use my calculator. So I'm just going to use base 10. So this is log 1024 all over log of 4. And now that allows me to use my calculator. Okay, so on my calculator, again, I just go log 1024 and I divide by the log of 4. Okay, and you can see that gives me a perfect value of 5. There's your answer. In the second one, okay, this 3 means I'm going to multiply by 3 at the end of the question. So it's 3 times, and this will end up being the log of 1 over 1,000, okay, because that is the argument in this case, all over the log of the base, which is log 2. Okay, and I've created a situation where I have a common base, which is 10, so I can use my calculator. So all I do on my calculator is go log of 1 divided by 1,000 and divide by the log of 2. Take that value and multiply by 3. So at the end I get negative 29. To 2 decimal places, this will be 90. Okay, so try that and make sure that you are able to do that. Okay, don't just copy down what I'm doing. Maybe pause the video and try it. But we need to make sure that we know the correct keystrokes to get that answer. Okay. In the third one, the log base 6 of 216 is an exponent. So it's going to be 6 to the exponent of, and that exponent can be calculated by going log 216 all over log 6. Okay, so that's my exponent. Okay. So what I'm going to do is I'm going to go log 216, so log 216, and divide by the log of 6, okay, which ends up being 3. So this is 6 to the exponent of 3. So log 216 over log 6 is 3. And we know, what's going on? Sorry, this will be 6 to the exponent of 3. So 6 to the exponent of 3 is 216. Okay, last one, D here. So in this one, again, I have a base of 2, and this square root of 1 over 1024, that whole thing is the argument. So you unfortunately have to go log of square root 1 all over 1024. Okay, and you're going to divide by the log of 2. Okay, so just a lot of calculator keystrokes here. So what I would probably do is go 1 divided by 1024, take the square root of the answer, and then log of that value. So there's the numerator, and now divide by the log of 2. Okay, and this gives me a perfect value of -5. Okay, so again, try those as we're working through them. Make sure that you're okay or comfortable with the keystrokes. And the basic idea again here is that I'm changing all of these log expressions to log expressions that now have a common base. And again, in these questions, I've used base 10. That's why you don't see a base in any of the calculations I've written. Right? Moving on. Now it says, consider the function f of x equals log base 7 of x. Explain how to use a graphic calculator to produce the graph. So if I wanted to enter this into my calculator, okay, this function right here, how would I do it? Well, I'd go to y1 in the y equals editor. And again, using the same basic idea we just done, I would enter the log of x all over log 7. Okay, so that's how you have to input into your calculator as a function for it to produce a graph. B says sketch the graph on the grid provided, label any x-intercepts. So as I go through, okay, and I'm entering this into my calculator, and I produce the graph. Again, it's going to have the same general shape that a log function has. Okay, so it comes up very close through the x-axis, okay, and grows up and to the right, like so. I now want to calculate what the 0 or the x-intercept is. Okay, so I do that using my calculator, using the 0 feature, and you'll see that that value is 1. Okay, so again, remember, we can also do that algebraically by letting the value of y equal 0. Remember, I want an x-intercept to let y equal 0. So if y is 0, 7 to the exponent of 0 is 1. Okay, so that gives me my x-intercept that I have on the graph. Now, C says use the calculator to solve the following equations. So if I was to solve the following equations using my calculator, okay, now I have log base 7 of x is equal to 5. So what I would do is I would graph y1 as, log x over log 7. Okay, so that's the first function. And now because I have a function on the other side of the equation, I would graph that as y2 is equal to 5. And I would obviously want to know where those two graphs do what, okay, and that's intersect. I want the x value of where they intersect. So when we do that, let's see. So they're going to intersect, okay, enter the two functions into your calculator. Okay, so y1 log x over log 7, y2 5. Find where they intersect, okay, and they intersect at an x value of 16,807. So you're obviously going to have to alter your window settings and go quite a bit further to the other side of the right-hand side of the x-axis to see the solution. In 2, okay, if you want to solve it basically using the same method we did in the first one, what you would want to do, okay, is you would basically want to move this 9 to the other side of the equation. Now, you could solve it by graphing everything as one function and just looking for the x-intercepts, but again, if I solve it the same way I did in the first one, what I would do is I would graph the following equations, okay? So for y1, okay, you could graph 3 times, okay, and then go log x over log 7. And you could graph y2 as 9, okay? That's one option, okay? Or if you really wanted to, you could divide both sides by 3. So then you would have y1 is just log x over log 7. And then y2 would now be 9 divided by 3, which is just 3, okay? So again, in either of those scenarios, what you're going to do, again, is want to see where the two graphs intersect. Okay, and you're going to want the x-coordinate of where they intersect. So they're going to intersect at an x value that is equal to 343. So again, please try both of those and make sure that you are comfortable graphing and finding the intersection points of those two functions. D now asks me to basically do the same two questions, but by converting to exponential form. So they want me to take them and solve them basically algebraically. So in the first one, I have log base 7 of x is equal to 5. So I want the value of x. I just convert to exponential form. 7 to the exponent of 5 is equal to x. So now in my calculator, I simply just go 7 to the exponent of 5, which is 16,807, right? So 16,807 is equal to x. And again, you'll notice that's the same answer, okay, that I got when I solved it graphically. Okay. The next one, same basic idea. I'm going to solve that one by converting to exponential form. So if I started from the very beginning, okay, so 0 is equal to 3 log base 7x minus 9, okay, I would take 9 to the other side, 3 log base 7 of x. Now divide both sides by 3, so you do have 3 is equal to log base 7 of x. Now I can convert to exponential form, so 7 to the exponent of 3 is equal to x, and you'll see that that is 343. Okay, there's my answer, and again, that is the same thing that I got when I solved it graphically by finding the intersection points. All right? So that's it for that lesson, you guys. A lot of stuff there. Again, I'll give you a day or so to work on that, practice it, make sure you're comfortable with it. Again, any questions that you have, email me. I will get back to you, and hopefully these lessons are making sense, and it's helping you guys kind of work through these a day or 2 days for each lesson. Okay, good luck, and I will talk to you guys soon.